right, so we've got our derivatives overview class today. So we're just going to be practicing using all of the derivative rules that we've learned in combination. On Friday, we're going to review for a test, and Monday you'll take test 2. Yeah, then Monday you'll take test 2. Okay, so we're going to have a quick look at the strategy guide for differentiation. Quick pop quiz, group pop quiz. Okay. Derivative of x to the n. Power rule, right? And x to the n minus 1. Derivative of e to the x. Derivative of a to the x. Yeah. Derivative of sine x. Cosine x. Derivative of cosine. Negative sine. Derivative of tangent. Secant squared, yeah. Derivative of ln x. 1 over x. We just learned that one on Monday. The derivative of arctan. Yeah. And the derivative of arcsine. That one had a square root. And it was 1 minus, right? 1 minus x squared. Okay, so those are all the derivative rules we know. Okay. There's a actual filled in version of that chart on the front page of your packet that you actually will be allowed to use on your test. So let's just take a quick look at what you're allowed. Yeah, so you can bring this page with you to the test. See, it says for use on the tests. Right? So you can bring this and your 1 page of your own notes. And if you rip this off, it has a front and a back, so you can use both, right? Strategy guide and the formulas. Okay. If a function doesn't look exactly like one of those functions, if you're trying to differentiate not the sine of x but the sine of some other stuff, right? You're going to have to apply another rule in conjunction, right? Instead, we need to use 1 or more of the following 5 rules to break our function down until it looks like exactly like one of the formulas above. So here's our what to look for in the following order. Sums and differences, if you're just adding or subtracting 2 functions, you can take their derivatives separately. Okay, most of you do this automatically at this point. Yeah. And then the constant rule, if you have a constant times a function, you can just copy the constant and take the derivative of the function. So there are some of you, a whole bunch of you actually, who I often see trying to take the derivative of this by using the product rule. And it will come out the same, but you don't have to do that, right? It will come out the same if you do first times the second plus the second times the derivative of the first. But the derivative of the first is always going to be 0, and so that whole term will just go away. So you can just take a little shortcut and say that's the same thing as c times f prime. Okay. However, when you're multiplying 2 functions together, right, if the first or the second is not just a constant, then you got to use the product rule. Do that when 2 functions are being multiplied together. Okay, a couple of cautions on the product rule. Remember that the derivative of f times g is not f prime times g prime. Got to write out the whole product rule. Caution number 2, expressions like cosine of 3x is a composition. That doesn't mean cosine times 3x, right? So saw a couple people making that mistake in some of the more complicated questions last class. If there's a product in the inside part of the function, you're going to have to use a different rule before getting to the product rule. We'll do some examples like that in a minute. And then we've got the quotient rule. When you're dividing 2 functions, do the quotient rule. Remember that the derivative of f over g is not f prime over g prime. It's this whole formula. And if the quotient is in the inside part, you're going to have to use another rule first. And finally, the chain rule, right? This is for compositions. You want to take the derivative of f of g of x, right? So we've got g inside and f outside. Start by taking the derivative of the outside function, evaluate it at the inside function, and then times the derivative of the inside function. Just a parentheses there. This can also be expressed using Leibniz notation, but I didn't see anybody grab on and really like that one. So you can stick with this one. All right. So some examples. X to the fifth plus sine x. We've got two terms, right? Added two functions being separated by addition. So you can just take the two derivatives separately. 5x to the fourth plus cosine x. 3x to the fifth. This is a constant multiple rule. That's 3 times x to the fifth. So you can just copy the 3 and then take the derivative of x to the fifth. 5x to the fourth. And then when you simplify, it becomes 15x to the fourth. X to the fifth times sine x is a product, so you have to use the product rule. X to the fifth over sine x, quotient, use the quotient rule. The sine of x to the fifth. That one is a composition, so we use the chain rule. That's the sine of some stuff. So we take the cosine of the stuff and multiply by the derivative of the stuff, which is 5x to the fourth. And then sine of x raised to the fifth, all raised to the fifth, right, is a little bit different because now the fifth power is the outside function and the sine is the inside function. So you start with the power rule, right? You bring the 5 down, copy the sine, reduce the exponent by 1, then multiply by the derivative of the inside function, cosine x. Then you would start with the product rule, right? If I had a 3x right here, right? I would start with the product rule first times the derivative of the second, and when taking the derivative of the second there, I would have to apply the chain rule. Yeah. Plus the second times derivative of the first. That's a good question. So those are the kinds of problems we're going to work on today, where you have to use multiple rules in one problem. Like in this next example, tangent of x over x squared times e to the x. So this is a quotient and a product, right? There's a product within the quotient. So I would start with the quotient rule, but when you get to the part that says the derivative of the denominator, you're going to have to use the product rule to take that derivative. So we start with the quotient rule, which is denominator, right, times the derivative of the numerator, which is secant squared x, minus the numerator, tangent x, times the derivative of the denominator, right? And when I did the derivative of the denominator, that was a product. So I applied the product rule there, all over the denominator squared. All right, again, here we have a product rule and a chain rule together. E to the x times the sine of 5x. Start with the product rule. So I have first, sorry, I did the sine of x times the derivative of e to the x plus e to the x times the derivative of sine x, which I had to use the chain rule to figure out. And then here's a composition inside a product. This is the ln of some stuff. So its derivative should be 1 over the stuff, 1 over x to the fifth cosine x. But then the derivative of the stuff, right, my stuff is actually a product. So I had to use the product rule to get the derivative of the stuff. All right, so let's do a couple of tough ones together. So g of x is the square root of 2 raised to the x ln x. Okay, so square root of 2 is a constant. Constant, the derivative of constant raised to a power is, yeah, times the ln of the constant, yeah. So that's a to some stuff, right? A to some stuff. So my overarching rule here is that the derivative of a to the x is a to the x ln a. But I don't just have an x up there, I've got some stuff. Okay. So I'm going to write out square root 2 to the stuff times the ln of square root 2. But then I still have to multiply by the derivative of the stuff for the chain rule. So the main rule is the a to the x rule. That's a constant to some stuff. That is a product rule, yeah. So I didn't actually write down, I didn't actually take the derivative yet. I just wrote down the main rule, and then I said times the derivative of this stuff, right? And for me, I find it helpful when you're doing a bunch of different rules all at once or in the same problem to not try to do them all at once and just do one rule at a time. And I said, okay, apply the main rule, and then I'll do the chain rule part after. Okay. So in my next line, I just copy all the stuff I already have. Okay, now I'm going to put a big parenthesis here because x ln x is a product, and the product rule is going to end up having two terms, and I want to make sure that all of this all gets multiplied by the entire product rule. So my product rule is first times the derivative of the second plus the second times the derivative of the first, which is 1. Yeah, ln x plus 1. Yeah. Yeah, so you can simplify this a little bit. X times 1 over x is 1. Ln x times 1 is ln x. Right here, that part. So I'm applying the product rule to x times ln x. So this is first times the derivative of the second plus the second times the derivative of the first. So the plus is, where does it say that? The product rule, it definitely says plus on mine. Okay. Yes. Yeah.
Is there a certain time that we have to like rotate derivative of this to dx instead of using like
No. Nope, doesn't matter. No. Nope, ddx and prime are totally equivalent notations. So actually, in the next one, if I come up with a up, there isn't anything else. Oh, because you can't see. Is that better? Okay. In the next one, I'll use prime notation when I write down a derivative. Okay. All right. Y is e to the cosine of the ln of x squared plus 1. That's a lot of compositions. So I'm going to be using the chain rule over and over and over again. But the main derivative rule is that this is e to some stuff, right? So that's the first rule I'm going to apply. The derivative of e to some stuff is e to the stuff. But then I still have to multiply by the derivative of the stuff. Okay, so the derivative of the stuff of cosine of the ln of x squared plus 1 prime, right? The derivative of the stuff. Usually I write d dx of the stuff, but you can use prime too. I think I'm going to run out of room. I'm going to put this all in a nice new page. Okay. All right, so in my next line, just copy the stuff I already have, e to the cosine of the ln of x squared plus 1 times. All right, so now I'm trying to take the derivative of the cosine of the ln of x squared plus 1. So ultimately, think of this as the cosine of some stuff, right? The outermost function is cosine. And what is the derivative of cosine? Negative sine. So this is going to become negative sine of the stuff, which is the ln of x squared plus 1. But then I still have to multiply by the derivative of the stuff that was inside, right? My cosine was my outside function. My inside function is the ln of x squared plus 1. So I multiply by the derivative of the ln of x squared plus 1. The derivative of the inside. All right, in my next line, copy the stuff I've already done. Times negative sine times the ln of x squared plus 1 times, okay. So now my outside function, this guy I'm trying to take the derivative of, its outside function is ln. Inside function is x squared plus 1. What's the derivative of the ln of some stuff? 1 over the stuff. So this is going to be 1 over x squared plus 1. Then I still have to multiply by the derivative of the stuff. So I have to multiply by the derivative of x squared plus 1. Okay, this should be my last line. Copy the stuff I already have. E to the cosine of the ln of x squared plus 1 times negative sine times the ln x squared plus 1 times 1 over x squared plus 1 times, all right, what's the derivative of x squared plus 1? 2x. 2x. And that's it. There's no complicated rules in taking the derivative of x squared plus 1. It's not a composition, not a product. So I just write down the derivative and I'm done. Any questions on that one? I'll put it back in a second. All right, so your group activities for today and your homework for tonight is 1 through 73 odd from pages 180 to 181 of your textbook. I also have a scan of it on the next page in your packet. It might take you several days to get through the assignment. It's kind of a big one. Check your answers with the answer key as you work through them. Recognize that you may have the right answer, even if it doesn't match up perfectly with the answer in the key, because there's some simplifying that might have happened. And remember that on tests, I do not require you to simplify. Okay, so there's one quick way to see if your answer and the answer are the same. If you graph them both and they have the same graph, you know that they're the same. So that's the one way you can check. The solutions, not just the answers, are in the solutions binder in the Math Studio if you get stuck on anything. The answers are, yeah, not the solutions though, yeah. Yes.